Hello everyone, I'm Giuseppe Raffa, and in this video I will present our paper on CloudFlow, a framework to statically detect security-sensitive data flows in serverless applications. Serverless computing platforms provide developers with services managed by a cloud provider. As a result, enterprises can focus on the development of the business logic of their applications. These consist of functions, also called handlers, that interact with the available services, such as data storage and database solutions. The key advantage of the serverless model is that the cloud provider takes care of the infrastructure, including issues such as scalability and maintenance. However, securing serverless applications is a complex task, and this is where our research comes in. Differently from previous studies, which are mainly focused on dynamic information flow approaches, we propose a static analysis technique. Our key motivation is that this type of analysis allows inspecting an application before its deployment. However, analyzing serverless applications statically is challenging for three reasons. First, they are event-driven, which means that their interactions with the cloud platform have to be considered. Second, multiple mechanisms can be used to define the application permissions. Third, the platform services code is proprietary and cannot be analyzed. To overcome these challenges, our paper presents a framework to identify security-sensitive data flows. We evaluate this with a new suite of micro-benchmarks, and we finally analyze a set of real-world applications. To better illustrate our challenges, let's consider a motivating example. This simple application has a user-controlled entry point, the HTTP POST request, which triggers the execution of four lambda handlers. The first is triggered by the HTTP POST request itself, and it sends a message to a queue. As a consequence of this, the SQS service executes the consumer handler, which calls the API upload file. This raises an event and triggers the execution of the third handler, which in turn updates a database. The fourth handler is finally executed, and it passes a string initialized from the new database item to os.system. The problem is that part of the information provided by the user in the HTTP POST request is used in the last handler to run a system command. This means that the application includes an event-triggered data flow that leads to code injection. The key observation here is that a general-purpose static analysis tool wouldn't be able to detect this vulnerability because it wouldn't consider the effect of the triggered events. So how does CloudFlow work? We combine information extracted from the infrastructure and the application code. This is necessary because the infrastructure code specifies permissions, events, and handlers-related parameters, indicated as PEH in the diagram. Our pipeline then analyzes the application code. By processing its abstract syntax tree, we first identify the Cloud API calls. We then analyze these with models that identify their security-relevant inputs. All this is using the CloudFlow representation, which allows us to instrument the application code and obtain a synchronous-like program execution flow. The important implication of this is that the instrumented code can finally be inspected with a general-purpose tool capable of detecting data flows, for example, PISA. Considering the importance of the CloudFlow representation, let's analyze how we instrument the upload file API call in our motivating example. We start with the initialization of the event object, which contains an approximation of the encapsulated data structure. As you can see, this includes the event name, extracted from the infrastructure code, and the cloud-based repository name, obtained from one of the API inputs. We then synthesize the call to the event-triggered handler, which has the event object among its inputs. The call is finally injected after the Cloud API to emulate a standard function call. Since the current implementation of CloudFlow is focused on Python, the framework also adds a type annotation to increase the accuracy of the results. So, how did we evaluate CloudFlow? Since all the existing serverless benchmarks are focused on platform performance and cost effectiveness, the first step was the development of a Cloud Bench, a new suite of security-oriented micro-benchmarks. Cloud Bench includes 40 AWS Python applications. 30 of them are interprocedural, whilst 9 are intra-procedural. The interprocedural ones include data flows that begin and end in different handlers, and they always contain event-triggered code. We make this choice to enhance the quality of our suite, as interprocedural data flows, as shown by our motivating example, are hard to detect. Regarding the vulnerabilities included in Cloud Bench, we have 27 cases of code injection, considered by industry experts as one of the most critical risks for serverless applications. As for the results of our evaluation, our framework passes 37 micro-benchmarks out of 40. The analysis of the other 3, detailed in the paper, shows that we have one false positive caused by a CloudFlow limitation and 2 false negatives due to the underlying static analysis tool. We also analyze 104 real-world applications to investigate the types of vulnerabilities that can affect them and to evaluate our framework more comprehensively. CloudFlow detects 205 security-sensitive data flows in total, which were validated manually. As shown in the table, 11 of them are actual vulnerabilities, whereas 64 were categorized as potential. We adopted this classification when, for example, the number of involved function calls was high. In the remaining 130 cases, we found evidence that the data flows were not a security concern. So, what kind of vulnerabilities did we find? The table shows 3 types. The first is code injection due to unchecked command line parameters. The second is also code injection, but caused by a HTTP request triggered data flow, which is the scenario described in our motivating example. The last 4 vulnerabilities, classified as exception traceback leakage, are significantly different. For this reason, we present an example in the next slide. The code shows a function and runs a set of commands after the try statement. If an exception is raised during their execution, the traceback object E, which contains detailed information about the exception, is returned as part of the HTTP response. This is not directly exploitable, but the pattern should be limited to the testing phase, because an attacker could benefit from it. The last observation is that this is a case of intra-procedural data flow. All the other vulnerabilities, except for one, are instead inter-procedural. One of them is illustrated in an additional case study included in the paper. As a part of our evaluation, we also measured the execution times. The diagram on the slide shows both the total and the CloudFlow specific execution times as a function of the number of lines of code in the repository. The total execution times start increasing when the number of lines of code reaches the approximate value of 3000. The CloudFlow specific execution times don't show the same trend though. This means that the increase is caused by the underlying static analysis tool, which performs the computational intensive task of identifying the data flows. To evaluate the overhead caused by our framework, we also analyze the percentages of the CloudFlow specific execution times with respect to the total. The box plot with the interquartile range shows that for 75% of the analyzed applications, the overhead is 12.8% or less, a generally acceptable value. So, what are the key takeaways of our work? We present a novel framework to statically identify security-sensitive data flows in serverless applications. CloudFlow constructs a synchronous representation of such applications by combining information extracted from the infrastructure and the application code. We also release a new suite of reusable, security-oriented micro-benchmarks, CloudBench, used to evaluate CloudFlow. Our framework passes 37 out of 40 micro-benchmarks. Finally, starting from a recent dataset, we analyze 104 real-world applications, where we identify 11 vulnerabilities in total. In the future, to conduct a more comprehensive analysis, we intend to increase the number of supported cloud services and APIs. We would also like to integrate an API documentation processing framework to automatically create API call models. Finally, we plan to use alternative underlying static analysis tools to support different languages. Thank you very much for listening.